Hello everyone, welcome to the fourth lecture of week 9. So in this week we have been discussing about prompting, and during prompting we discussed how you can actually make use of external tools like computer programs and search engines, right, to get a better output. And we saw that in the context of prompting. So I'll have this one lecture devoted to how do you use external tools with language models. Okay, so we'll briefly discuss various popular techniques in this scenario. So we'll talk about why do we require to use tools with language models, what is the need for augmenting language models with tools, and we'll talk about two different frameworks, so tool-aided language models and Toolformer, and this is where we'll go in detail. So how does Toolformer actually work, and how do you actually call different external APIs. So we'll go in detail about Toolformer. So why do we need tools? So we have learned about language models as some very powerful text generators, right? So you can use a decoder model or encoder decoder model, given a context, given a prompt, they can generate output. Now where do they actually fail? So there are two very specific scenarios where LMs have been shown to be failing not up to the mark. One is complex reasoning, which also requires some sort of, say for example, mathematical reasoning. So that is somewhere that language models struggle, and also how if you have to access real world information, right, you have to reason some way, you have to talk about today's date. Now this is a fundamental limitation because LLMs are typically only trained up to a certain data, right. So you are trained on certain data which is up to a certain amount of time. So you are not able to get the real world information that is after that pre-training data. So you need to typically augment it with external tools so that you can get real world information, and that can be used by the LLMs, okay, to actually cater to a question that requires real world information. Same goes for complex reasoning. Maybe I can add certain tool, like here you can see, so you can extend language model and get time, say what is the current time in the real world, right. So you can get the time at any moment and you can make use of that. Similarly, you can say multiplication, square, you can just make use of a calculator, because it has been shown that LMs have not been too good at with numbers, multiplication and all, they make mistakes. So can I use a calculator? Now these are along the spirit of what we already saw in the last lecture, that you can rather than actually doing calculation, you output a program, computer program, and let a separate compiler and executor run that program and give you the final result. Similarly here, why only programs? You can actually use multiple other kind of tools, right? So what is the basic tool use paradigm? So you see, by default LMs will do next token generation in autoregressive mode. So they will keep on generating one token at a time. Now that means if I have to use a tool, I have to switch between text generation mode and tool execution mode, right. So at some point of time you should move to, okay, now I am calling a tool, I get the output from the tool and I go back to generating next words, right. So, and you can do learning by inference time prompting, and you can even do learning by training, and we will see some example of learning by training in Toolformers. Now this is one example of the tool usage. So your question is, how is the weather today? Now the LM will not know it by default unless you have some external tool that can say it is. So this is the autoregressive generation, text generation, it is. And then you have to have some idea that for this question I need to call an API, so check weather, right. And this will actually call a remote server, call this API, get the output that it is sunny today, and I mean it will get the output, say sunny, the current weather, and you will replace sunny, it is sunny, and then you will continue. So sunny is an output of the text generation itself, which is coming from the external API, and then you continue generating, right. So you are switching between text generation and calling API, getting the output, putting it back and continuing your generation. Right. So, end user may not know that you have called an API, right. So, this is all internal to the system that you are calling API, getting the output, but then this is what you present to the user. It is sunny today, and it appears as if you have direct access to the real world, but yeah, you have it through an API of through certain APIs. Okay. So, LM will replace the API called tokens in the response of the user. So, in general what I can say, so an LM used tool is a function interface to a computer program, a separate program that runs external to the LM, right. So, it is not internal to the LM, LM will just call this. So, LM generates the calls, right. So, it generates token, it can also generate the call. That is one of the very interesting idea, that if LM can actually generate token, it can also generate a function call. Now, once it generates a function call with all the arguments, parameters that are required to use the tool, it fetches the output and uses that to replace in its current generation, right. Now, I will talk about this work briefly and then go to Toolformer. So, this was tool-augmented language model, TALM. So, it says, okay, in general you have language model where you are given an input and you can produce an output. So, what we will do in tool-augmented language model, so we will have somewhere we will have a tool input. So, we will call an external tool with all the required parameters, we will get the tool result, right, and then using that we will continue our output, right. So, this again becomes internal to the system. You may actually see what tool has been called, what is the output, but you can just simply see what is the input, what is the final output, right. Like take an example. So, this is a text to text interface, right. So, you have suppose this is your input text, right. It can be question answering, it can be summarization, whatever, right. So, typically question answering is one task where you will need tools more often than something like a summarization task. So, then what you will do, you will have something like, okay, I want to call a tool with all the required parameters. So, these are all the parameters or arguments that are required for the tool, and then I say, okay, I need the result. Now, this is how you call a tool, and whatever is the output you put it after real. So, this is the tool output, right, and then you say, okay, this is my output, the language model output, and this is the actual output. So, this is the tool output, it will have to reformat it as per the requirements and get you the final output text. So, by default LM was only going from task input text to task output text, right. Now, in between you have this additional steps where you call a tool by putting all the arguments, you get an output result, and based on that you continue your generation. So, what TALM does, it first generates a tool input condition on the task input text and invokes a tool's API by generating a delimiter such as result, right. So, like this is my task, how hot will it get in NYC today, that is my question, right. So, you say, okay, I'll have to call a tool weather and look up a region like NYC, and you get a result like precipitation chance 10, high temperature 20, low temperature 12, right. And this is the output from the tool. Now, you have to use this output to generate your final output. So, this is the LLM output, that is today's high will be 20C, right. It could not have got it without referring without actually calling this API, but that is the process. I see it is not too difficult, but it is very important, I mean in terms of the functionality of language models, that you can actually call various tools, get the output, get the tool outputs, and use that to generate your output, right. It has some similarity to how you do say retrieval augmented generation. So, you retrieve certain things based on your query, use that to do your final generation, right. So, now you are retrieving from an external tool here. Yeah. What is interesting is that you generate this call yourself. So, this is what the LM will generate. So, what is the tool I have to call and what are the input parameters that I have to use, right. So, whenever you detect this result, so you append the tool output, this is the tool output that you are appending after result, and then TALM will continue to generate the final task output. This is the task output. So, for the end user you may even skip everything. So, you can skip everything. So, you will only have how hot will it get in NYC today, and the output is today's high will be 20C, right. And everything else is happening internally by calling API, getting the output and then using it to generate. Okay. And what's the interface? Like this is the Math QA dataset example. So your question is, if Lily's test scores are 85, 88 and 95 out of 100 in 3 different subjects, what will be her average score? Right. So you know, okay, for solving it, what do I need to do? I need to add these 3 numbers and then I have to divide whatever is the result by 3. So you say I will call a formula for doing that. So once you call a formula, you get the result. So after result, you will append the output. Now to the user, you may not want to give all these like decimal points. So you say, okay, my output is 89.33. That is coming directly from here, right? So this is how you can call tools. Now we will go a little bit more in detail, like how exactly do I train a language model to use tools, right? And we will take this example of Toolformer. So language models can teach themselves to use tools, was the title of the paper. Okay, so what this LM does, this Toolformer, it autonomously decides to call different APIs, right? So it can call a question answering system, a calculator, a machine translation, and a Wikipedia search engine. It can call at different point of time while generating, so that it obtains information that is useful for completing text completion, right? So the final goal for an LM is to do text completion well. It can make use of external APIs for doing this. And here's an example, right? So now the New England Journal of Medicine is a registered trademark of, right? And now you have to answer this using an entity that you may not know. So what you will say, okay, let me actually ask a question. So my question is, who is the publisher of the New England Journal of Medicine? I get an answer, and using this, I do my completion, the MMS, right? Out of 1400 participants, 400 are. So you want to write what percentage of these are 1400. So you create a formula. So I want to call calculator, 400 divided by 1400. So this will give me 0.29. So this is 29%. Pass the test, right? Similarly, the name derives from La Tortuga, the Spanish word for. So you want to translate to English, the Spanish word for turtle. So you get the output from machine translation and you get turtle. The Brown Act is California's law. Now you don't know what that law is, so you do a wiki search, Brown Act, you get some output, use that to do your completion, right? And that's the essential idea. And you see, this actually gives a lot of other functionalities to the language model, right? Now question is, fine, the language model has been trained only for next token prediction, right? So how would you actually train it, or how would you modify it so that it starts calling these APIs, right, while doing generation? So how do you do that? Now that is what is interesting framework that Toolformer came up with, right? So first of all, how do you represent an API? So this was very simply done. So any API call will have a tuple AC and IC. So AC is the name of the API and IC is the corresponding input. So whatever input you need for an API, like for translation, you need the source text, right? So C is the, you can say, API name and the input. So this is one thing. Now once you call an API, you will get the result. So R is the corresponding result. Now, and this is how you can call the sequences. So this is EC, just the call without the result is start with API, and you see they simply use for API. I mean, while they were using API like XML codes for in the paper, in the actual code they have just used the open bracket and this is the closed bracket, right? But we will simply go with API open and API close, right? Now how will they represent it? So they will have an open bracket, then the actual name of the API. So then you have a again parenthesis, what are all the input parameters for this API, close parenthesis, then you close this bracket, right? And for the result, you have a right arrow which they represent as simply like this, right? So, and they say the reasons for doing that is that they didn't have to change the vocabulary, right? So without modifying the vocabulary, which could have been much more tedious, as we have seen in one of the lectures. So they didn't modify the vocabulary, they used whatever tokens were there already, and they devised this particular schema for calling an API, right? So that means if you really know how to call an API, you can use your own vocabulary, right? Now the question is, how do you make it learn that, okay, at this point I have to start putting in open bracket and call an API, right? And so see, once you call an API, other part is easy, then you can just simply execute it by certain interface, get the result back. So important point is, while doing generation, find out at what point should I call an API, right? That's the idea. So at what point should I generate this open bracket and then the API. Okay. Now what they did, they actually created a training data for this, and that makes sense, because if you train it for some data where it is calling APIs, it will learn how, I mean, in this scenario I will call API, in this context it's better to call API, right? The problem is that you may not have it in data like that, where the LMs were calling APIs, right? So this is a good use case, but you may not have training data. So they did some very interesting, they had some very interesting idea for creating this training data, right? So what they will do, so they will have a data set of plain text only. Now they will convert it to a data set augmented with API calls, right? So that was the most interesting part of this paper, that they will take any data set and they can augment it with API calls. How exactly? So they will say, okay, let's have, so you have a given text, like the Pittsburgh is also known as the Steel City. That's already known to you, right? Now what you will do, you will say, okay, we will go through each step in detail, but the idea is that at any point of time, let's say after I-1 tokens, you will find out, okay, can I sample some API calls at this point of time? So let's say I sample 2 question answering here, right, for generating I to N. What other name is Pittsburgh known by, and which country is Pittsburgh in? Let's say these are 2 possible questions that you can sample. Fine, once you have the API calls, you execute the API calls, you get a Steel City and United States. Then you say, if I provide the question and the answer, right, the API call, the question and the answer to the language model as a prefix, right, along with whatever it has generated, will it give me a higher likelihood for generating the remaining words, or will it give me a lower likelihood? That it was as simple as that. If you prefix this information before the current input, will it give me a higher likelihood of generating this, right? And they actually formulate using the loss. So if so we filter out the calls which do not reduce the loss over the next tokens. So you should reduce the loss over the next tokens by putting this as a prefix, right? And that's how they sample, and whichever actually reduce the loss, they will keep it in their data set. I mean, they will augment the original sentence with Pittsburgh, also known as, and you see now you have an open bracket, a QA, I mean API call, the actual question, the inputs, and the right arrow, so it will be the output, Steel City. Now this is the augmented data set. Now if you train LM on this data set, you will know, okay, at this point I should start having a high probability for open bracket, and once you have an open bracket, you will have a probability for calling certain APIs, right? So you can have some probability distribution over APIs, and you will just start generating this. Okay, so let's look at this process in a little bit more details. So how do you sample API calls? Like, so that's where they make use of prompting, right? So because LM may not know how to sample API calls, right? So how do you say, like, I will call QA with this question, right? And the idea is I will make use of the in context learning capability of the LMs. So I will create a prompt. So what is a prompt? Your task is to add calls to a question answering API to a piece of text. The question should help you get information required to complete the text. You can call the API by writing QA question. Question is the question you want to ask, right? And you give an example, like for this input, you can say Joe Biden was born in, and you don't know where, so you will call QA where was Joe Biden born, and like, so it's only for calling in API, right? So you teach the LM through prompt that, okay, in context learning, so this is how you can call an API, and then you give your actual input, like the one that you had. Pittsburgh is also known as the Steel City. You give that as input, and the LM will generate an output. But what is interesting here, you don't worry about the output it generates, right? What you worry about is the probability distribution that it will generate, right? So given this input, now it will start generating a probability distribution where it can also generate these API calls, the open brackets and all, right? Now we will make use of that probability distribution. How exactly? Okay, so I mean, this is very fundamental. So let's say, so these are the tokens that have already been seen, n tokens, and you have the probability for the n+1th token, right, that a language model is assigning as a continuation for the previous sequence. So what they will do, so they say, okay, I can call API at any position in the text, right? So you say, okay, if I start from 1 to I minus 1 tokens as my prefix, and px is my prompt, right? So prompt is given, the whole prompt that we saw, this is given, and so some I minus 1 tokens of x. So what is the probability the language model is giving to start on FA? That means to an open bracket. What is the probability of open bracket after this? So you can compute it for all positions, right? It's not too difficult. At all positions, you can compute this probability, right? Because all the input is given to you, and then whichever like you would have a threshold. If this probability is above a threshold, you keep the positions. If they are too many, you keep only top k positions, right? So top k position that have this probability above a threshold, they are kept. So these are potential positions where you could have called an API, right? You don't know what API, but you could have started with this open bracket. Now what you will do? So for each of these k positions, I mean max k positions, you obtain AM API calls, right? So what does it mean? So you will have this prompt, I minus 1 token, and start, right? Start of the API. This is what is the input to the language model. Now it will do autoregressive generation, right? So it will generate certain sequence, right? So an API may not be a single token; it may be a sequence of tokens. So what you will do? You will generate a sequence of tokens, but how do you know this is an API, right? How would you stop? So that's why they use another trick, saying that okay, it will stop whenever it encounters an end of API. That means this token. So you start from here, keep generating until you get end of this API, and now this is whatever is in between. I mean, starting from open to close, that is your actual sample of what API you have called. API with all the input next, right? Now you have got these, for each position you have got up to m API calls, right? Okay, so it may be at most k times m, right? There are k position at most, and each position may have some m API calls. You can sample, right? You can do sampling, because you have talked about sampling method, so you can sample multiple sequences. I mean that means you will not go by greedy decoding here. Now, so and then once you have all these APIs, you will get a single text sequence as the output. You can execute these APIs. Once you have the API calls, you get the output. So what do you have now? So at each position, you have API call CI and also the corresponding result RI. Right. Now what? Now you say, okay, will I? So I'm still augmenting my data set. So I'll say, okay, will I use this particular CI/RI to augment my data set? So you say, okay, is this helpful or not? Is this API call helpful or not in this particular sentence? And we had a scenario, we had a particular constraint for that. What is the constraint? So we say an API call is helpful to the language model if you provide it with both the input and the output, and it will make it easier for the model to predict the future tokens, right? That's what we said. So that means, so we will have, okay, I'll feed the API call and the output as a prefix, right? And then I'll have the other tokens, and I'll find, I mean all the tokens. So this is up to I minus 1 tokens, right? I minus 1 tokens already there, and you put this as a prefix. Given this, you find the loss for the remaining sentence. This is simply cross entropy loss minus log probability of the correct token. So you get the loss after putting this as prefix, the whole, the call, and the result. Similarly, you get by putting nothing. I mean, you don't put anything, so simply all the I minus 1 tokens, and you start generating one by one. You get the loss from there, and you just do the call, not the result, the call. So P x now is just the call, all the I minus 1 token, and start generating, get the loss. And you say this Li minus is the minimum of these two things. I mean, not receiving this API call or just the input, and Ni plus h by putting both of these. Now I will only keep the calls for which Li minus Li plus is greater than a threshold, because my loss should decrease, right? Li plus should be smaller than Li minus for it to be useful. So I find the useful calls. So adding the API call in the result should reduce the loss by at least a threshold, right, compared to not doing the API call at all, or adding no result from it. So that's all. Now you have an specific framework by which you can decide whether or not to add this particular API. Now you have an augmented data set, so now you can wherever this threshold is passed, you augment the data set with this, and you fine tune your model with this. Right? That's as simple as that. Once you have this data set, and here are some examples like here the floating window in the Grade I listed church of Saint Leonard in Middletown is said to be the oldest war memorial in the United Kingdom, and then now you have an API call. Right, and you see the result actually is higher. 5.49 is the loss that you reduce, and you find it's actually useful, right? And this is similarly the WL will be open on Friday. You call calendar, so you say okay, it usually helps me to say today is Thursday, March 9th, so Friday will be March 10th, right? And Sunday so on. So like that, there are cases where it helps generation. Like here, you want to do some calculation, you call calculator API. So in all of these cases, the loss is reducing by calling an API, and you put that in your augmented data set. Okay. So what happens at inference time? Right, inference time. So you have to generate text. Right. So you have already been fine tuned. So you will keep on performing regular decoding until it generates the right token. That means it has also already mentioned the API call it needs to execute, and now it wants the result for that. So what we will do whenever it generates this right arrow token, so we interrupt the decoding process, call the API right, that is already generated, and get a response, and put it after this, and now continue decoding, right. So that's the idea. So we stop decoding only after this, because it has to first generate the API call and all the parameters, and then this for result, and then you stop, execute the API, get the result back, and now it will continue, right, inserting both the response and the end of API token. Okay. And these were some examples like question answering, where was the Knights of Columbus founded, and this is the output. This is the Wikipedia search that you call fishing reel types, you get this output. Calculator 27 plus 4 cross 2, you get this. What is the calendar entry, right, and machine translation and so on. So you can call various tools, and this is a very interesting framework. You can take an existing data set, augment it for using tools, and train a model for so that it can actually call tools at the inference time. And there have been many recent works that I have not covered here, but I mean this is a very interesting research topic, that how do you integrate multiple tools. Like this tool LLM talks about 16,000 plus real world APIs. How does LLM use that? Hugging GPT, right? So solving ADAS with ChatGPT and its friends in Hugging Face, and Gorilla, right, connected with massive APIs. So, and there are many more papers that have been coming up on this topic. Okay, and the various papers cited in the slides are the references. We will continue. We will have one more lecture for this week, right? We will talk about. We'll go back to prompt engineering and say, okay, how do you automate prompt engineering? That will be the topic for the last lecture of this week. Thank you.